All right, time to start again. Unfortunately, I could not get a hold of the administrator, so we will have to do the registration in the email kind of way. So send, if you're not able to register using Ladoc, send me an email with your name, your personal number, and the program you are attending. So I will compile this and forward it to our administrator this afternoon. I will be posting this also on the course homepage, so you can find the instructions there. All right, so we have done some repetition about where analysis and design fits into the development process. So next step is actually to assess why should we be doing analysis and design anyway. And I will start by showing a small example. So, anyone knows what that is? Yeah. Hexadecimal numbers. What are they doing? What's happening? What is this about? Yeah, it's something that is handled at least in memory. But this representation of a system is not that easy to understand. Okay? This is the representation of a system that the CPU wants. This is the actual machine code that forms an executable file on a Windows operating system. So this is what the processor wants. It can't read anything except this. It can't read requirements. It can't read if statements. It can read this. Working in this representation is doable. You can program in assembler, for example. But the scope of your project would probably be quite small. And it will take a long time to understand it if you need to debug it. If you need to come back to it and maintain it and add something, you will probably need a lot of time to understand this representation. But it is very efficient. It is the minimum, so to speak, that the CPU wants to eat. So instead, we don't actually work on this level so much. I don't know, have anyone programmed in assembler? Machine code? There are usually a few people somewhere that, yeah, it's my game. It's a game. That kind of like has a knowledge about this kind of stuff. So this is not usually what we expect when we get the software to maintain, for example. Hopefully we get something like this. You get some kind of code in a more high-level programming language that is at least readable to humans. But it's not really that easy to understand. And sure, maybe you can understand small bits of it here and there at a very detailed level. But looking at the source code like this, it's quite hard to get an overview. You don't really know how this particular class or function is connected to other classes or functions. And this is just a small sample of all the code that was used to form this machine code. So source code in a high-level programming language is good and essential for maintenance and development, but it is probably not enough if the scope of the project is big enough. Because you can't really get knowledge about how this system is structured, how these pieces are connected to each other. If I change something here, will it affect something else in the system? So this was a small example about how we kind of like go from a very detailed CPU level to a more high level in our development process. So, at this far side, as we saw, we have a CPU. I will make some kind of integrated circuit. And it should be a Motorola CPU. And as you saw, the CPU eats machine code. And this is ones and zeros that are put into memory, that are put into registers in the CPU, that are used as either instructions or data. That's all the CPU knows. It can add these, it can subtract, it can shuffle memory. That's basically what it does. And we also saw that, okay, this level of detail is not that fun to work with. So we have programming languages. So we can write code in a somewhat more high level that we can understand, that we can read. So we represent that by if statements. And luckily enough, we don't need to translate that into machine code ourselves. Rather, we have a compiler or an interpreter doing it for us. So, as we saw, the code was also quite detailed, hard to get an overview. Imagining several people working together to do something, you need to know where are you working, how should we divide our labor. So in any major engineering effort, you need some kind of blueprints. So we can do these kind of diagrams. That form a blueprint over the system. This can be very detailed. It can be almost like the source code itself. Or it can be on a higher level. So using the blueprint, you can produce code more efficiently and with higher quality. And talking about quality, you have such things as maintenance, for example. We need to maintain this. We need to change it. It must be changeable. It must be understandable. It must have high performance. Efficiency, we need to be able to coordinate our work. We need to be able to schedule 10, 20, 30 programmers to work efficiently in this. We need to know why we do things, so we don't do any unnecessary things. We need to standardize how problems are solved, so we can more easily change work tasks and implement stuff. You can also generate code from these kinds of diagrams. So you do your diagram and you press a button and plop, you get skeleton code. let's do it like that. So before you can do a blueprint, you often need to understand how you do things, or what you should do, and you need to understand the entirety of something. It's quite hard to just do a blueprint over very specific small parts and then combining them. It is more easier to get an understanding of the actual problem first and then develop a software solution for it. And this is the analysis part of things. And at the far left, we have this dude that has an idea. That's a light bulb. So he has an idea about something. He has a problem or an idea. I think this kind of system would be neat. I think this would be a good way for us to be more efficient in our organization. A good way to market our stuff. A good way to find our customers, help our customers. Some way to earn money. And these ideas are often expressed in requirements, sentences, text, maybe some images over how the dude thinks that stuff should work. Then we do analysis of this stuff to see how it fits together. And then we do a blueprint over that stuff to see how it should work in software. And then we do an efficient implementation of it. And then it is translated into a working representation that can be run on a CPU. And taking these smaller steps towards this very detailed representation from this abstract representation is easier than taking one giant leap right down into source code. And we can add things such as quality and efficiency on the way. Yeah, and also vice versa for many of these steps. Because if you let a problem, maybe here in the requirements, go all the way down here, which easily happens if you skip these steps. Okay, yeah, we go for machine code directly, from idea to machine code. It's very easy to make an error here. So if you make an error, you get a bug. Finding and correcting a bug in machine code is not that fun. So if we can spot the error in here, it is better. More efficient, easier to fix, and maybe even when the programmer gets the task, he can spot some mistake before it enters the product, which is more efficient. And even more efficient is, can we spot this error when we design our software? Okay, this won't work. It doesn't work like this. We need to change something. And if we can spot this error even before that, if we can spot a mistake in the requirements, some detail that is missing, already here, it is even more efficient. So this also gives us the opportunity to find problems, find missing details as early as possible. So this is called semantic gap. The difference between two representations of a system. And typically we want small semantic gaps all the way. So we want to take small steps towards the executable system and not one giant leap. And as I said, blueprints are required in all professional engineering efforts, software also. You can, of course, produce working software without blueprints, but it will probably be harder for you and less efficient. And the scope of a project will probably be quite small. There are examples from engineering efforts that are done without blueprints. I don't know if you have heard about the Winchester Mystery House. Anyone? You can Google it anyway. But it's this beautiful house, and it was built entirely without blueprints. So you can, of course, accomplish big things without blueprints also. It's 160 rooms, 6 kitchens, 2 cellars, 950 doors. So it's quite big. But on the other side, it took 38 years to build the house. They had 147 different carpenters during this period. "65 of the doors lead to nowhere." $75 billion. And they have 13 unfinished stairs that you can probably fall down from and hurt yourself pretty badly. 24 lamps that were supposed to go in the ceiling are mounted in the floor. So without blueprints, you can accomplish big things, but expect it to take longer, expect it to cost more, and expect it to have many funky features that maybe are not that good. If you want to know more about the Winchester Mystery House, you can Google it, as I said. It's kind of a fun example, at least. So, all right, we know a little bit more about analysis and design. The next thing to know a little bit more about is object orientation. Why should we do object orientation? Why is it object-oriented analysis and object-oriented design? Basically, I will go through this a little bit fast, I think. The basis is that as humans we have 3 major things that we do to handle complexity in our lives. Our brain is wired to handle complexity, and we do it by doing abstractions. That is, we remove unnecessary details. When passing a street, you are really not that interested in the registration number of the car coming at you to hit you. You are more interested in big thing moving at me very, very fast. I better jump. You're not interested in that the driver is talking in his cell phone, or the color of the car, or the status of the left wheel. So, depending on the situation, we peel away details to get to the essence. That is abstraction. Encapsulation is the next step, or next strategy we have to handle complexity. How many of you have a driving license? Quite a few. How many of you actually know how a combustible engine works? 1, 1.5. We don't really care about how the car works when we are driving it. It's supposed to accelerate when we push the gas pedal, it's supposed to brake when we push the brake pedal, and it's supposed to shift gears when we want to do that, and it's supposed to turn when we turn the steering wheel. So we have taken a lot of complex stuff and hidden it away by encapsulating it in a standard interface. If you have a driving license, you can drive most cars. Maybe they need a little bit, you need a little bit of time to adjust to the particular car, but it's not much, and you know how to drive every single car almost. They have a standardized interface that encapsulate all this advanced technology that is in the engine. You don't need to know about the gearbox, how it works, or how the combustion engine works, or a lot of the stuff to be able to use it. And the third thing is the hard word. I hope I spelled that one correctly, probably not. Hierarchies. As humans, we tend to build hierarchies really, really quickly. So, there are two types of hierarchies of stuff. You can have whole and part hierarchies. That you know that a car is made up out of wheels, an engine, and a hull, seats, and a steering wheel. So we form this kind of whole and part hierarchy. We know that a tree is made out of roots and leaves and branches. And we know that a bush is made out of branches and leaves. And knowing about the leaves on the tree, we can reason about the leaves on the bush, because it's kind of like the same thing, but in another hierarchy. And we can reason about wheels on a bicycle, because we have knowledge about wheels on a car. The other type of hierarchy we build is a type of hierarchy. So going from a very abstract concept, I need to go from point A to point B. I need some kind of mode of transportation. I can step down and I can find different types of modes of transportation. I can go by car, I can go by bus, I can go by bike, I can go by train, I can go by plane. And I can step further and further down this kind of hierarchies. And those kind of hierarchies we make really, really fast also. So the main idea of object orientation is to support these three directly in the modeling and implementation efforts. So object orientation is done so it should be easier for you to develop. It will probably feel a little bit harder at first to get to know this. But basically, if you're making it harder, you're doing it wrong. All right. We have a few minutes left, so we will be doing an entire example, and we will be doing a requirement analysis, design, and implementation. Test and deployment will maybe be done a little bit later. So you get the whole course in about 10 minutes. My brilliant idea is the world is in dire need of a dice game. More dice games should be played to create world peace. So we have a requirement, play dice game. quite simple. The dice are rolled and the result is presented. If the result is, if the sum is 7, the player wins. Clear?
1 to 6 instead of that.
Yeah, that's a good question. We could maybe assume that it's 1 to 6. All right. Probably the most common dice. But you should not assume anything, of course. So we will be doing some analysis of this. Analysis is done by taking central concepts from the requirements and see how are they related to each other. Can anyone spot some kind of central concept in this requirement? Anything? Have a lot of activity in the chat. Who is this guy? Multiple attendees. Exactly. As stated here, you can look at substantives and verbs in the text. So, looking at the substantives, you have the concept of a dice game to begin with, maybe. So we put that one up. Yeah, nouns, it's called nouns. So we have dice game. Something else. Well, maybe we have some dice. Seems that is if we have a player. Yeah, we have a result. Maybe this is enough. Maybe we should not overdo it because we have kind of like one sentence of requirements and we already have 4 kind of big concepts here. The next step is to find how these are related to each other, to understand this requirement. So maybe you could just imagine this as a physical game. You have a box that is the dice game. And the dice game contains the dice. And the player rolls the dice. And maybe also the result is this a little notebook where you can write down your result. Oh, this time I got 57. I did not win. Maybe something like that. We have a sum here. I interpret that as the actual result. So, all right, looking at this, you can start thinking about, okay, the dice game contains dice. Maybe it's even called die in singular. But how many? 2 at least, yeah, probably, at least if they are 6-sided. So, okay, let's settle for 2. So we can write a small number there. This is a way that you can use the analysis model to visualize the requirements and see, all right, something is missing here. We need to know how many dice are in the game, because that was not stated also. And of course, you cannot just make your mind up. You need to go to your product owner, or stakeholder, or user and ask them. All right. The next step is to transform this model of reality, the analysis model, into working software. And the way that we do that is to look at the requirement, we look at the analysis model, and we form how the software should work. In the book, he likes to do a dynamic design first. That is, he likes to display the objects that are actually executing stuff and how methods and functions are called on these objects. And then produce a class diagram from that. Personally, I prefer to do it the opposite. What you prefer, you will probably get to know that during the course. But let's do it as by the book. So, we have this object, a player object, that represents the user interface of the application, the user interface for the player. And looking at the requirement, the first thing that happens is, okay, the player wants to play the dice game. That is what happens. We look at our analysis model. Okay, who should the player tell that I want to play the dice game? Well, we have this concept of a dice game. That sounds like a good idea. Okay, looking at the requirements, what's supposed to happen? The dice are rolled. Okay, we need die. Does anyone have knowledge about the die? Oh, the dice game contains the die, so it will probably be a good thing to let the dice game call that. On 2 die objects. So, okay, that's done. What are we supposed to do next? We need to present a result, and we need to calculate the sum. So we need to get some kind of value from these also. And then we can return to the user interface. Win, lose. So, all right, this is how the software is supposed to work. These are the objects that are created, the methods that are called to implement the requirement. Also looking here, we have 2 types of classes. We have the dice game, and we have the die. So we can dice game, make a static view over the system also. And we have a die. We have a method in the dice game class that is called play. I decide that it will be returning a Boolean. True if we win, false otherwise. We have a die that has a method roll and get value. And we also need to store this value between the roll when roll is called. So we need a member variable here. And it will be an integer. So we also need to connect the dice game and the die classes, because messages are called from the dice game object to die objects. So these need to be connected. And they are even named here. These objects have a name, M underscore D1, M underscore D2. So here we have a dynamic view, an interaction diagram to be more precise. Time flows downward here. Here we have a static view. We can see the classes that we need to implement. So maybe we have a few minutes to do this implementation. So, all right, you start with the dice game class. If you remember, it had two relations to the die class. These are implemented as member variables. Die, die. We had this play function, and it was supposed to roll. That's a little bit awkward in Java, needing to write Boolean instead of bool. MD1 get value plus MD2 get value. All right, everything compiled to start with. That was kind of a surprise. This, of course, role here needs some kind of random implementation, but I will do that later. We need some kind of way to play the game. So we got the user interface up and running. So then we need to create the dice game. And we will probably lose every time right now, because the value of the faces of the die are 1 when we roll them. So maybe we should just add the randomness here. Oh, I need to check out my cheat sheet. Hope to be able to win sometime. Yeah, that 1717 is just a big number. Ah. I think it should work. Probably it's just the randomness of things that is not working along with me right now. Yeah, a win! Yay! Very, very, very fun game. But as you can see, the implementation here is quite straightforward. Here we have the dice game. We create the dice. This is the focus actually of the design that we did, this method, where we do the roll and we do the get value. And this is also what you can see in the interaction diagram here. We have our classes implemented, dice game die, and we even did the user interface, the player. And this is the Java specific part. Mostly Java specific, because how does program start in Java? Yeah, well, you need to do this static public method called main and stuff like that. And in C# it's something similar. In other programming languages, you have other ways to actually run your program. And what I did here with the command line was just compiling and running Java programs. So you should be able to download the Java IDE and just do this yourselves with quite little effort. Or you can do the C# variant. It should look very, very similar to this. Questions? It's a line from that role should of course be like that. Thank you. Questions? All right, if you're not able to register for the course, send me an email and I will be compiling this. I will also be posting the lectures on the course homepage, the recordings, and it will probably be the live stream as soon as possible, and I will upload the recordings to YouTube for maybe more convenient viewing. You can fast forward a little bit easier and also run the presentation in 2 times the speed. It's really awkward to start with, but you actually get used to it. Yeah, I think I will be using YouTube. Yeah? Yeah, the question was if there are any reading instructions for the actual lectures, and there are on the course homepage. I will be posting for each lecture what chapters are discussed. And you can also watch the old homepage and check those chapters out, because it's 99% the same. You won't be able to find the recordings on the My Moodle. You will be finding the recordings on the course homepage in CoursePress. I think you have a link to the CoursePress homepage in the schedule. I think it is. It is. Okay, this is the old homepage. Here you will be able to find it. Yeah, see you guys on Wednesday, and as I said, send me an email if you are not able to register, so I will forward this to our administrator. Bye for now.